Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is experimental verification of both Thevenins and the Maximum Power Transfer Theorem. Today's lecture has two objectives. First, we'll use circuit theory to calculate the Thevenins equivalent of a complicated circuit and predict its behavior in response to changing load conditions. Second, we'll verify our calculations by building both the original and the Thevenins equivalent using real-world components in common electrical instrumentation. Ideally, both the original and Thevenins equivalent will behave identical to each other. The intention of this 1-2 punch is to prove to you, yet again, that I am not some dim-witted peddler of nonsense, and the skills and theories I'm presenting are real, demonstrable, useful, and most importantly, true. This lecture operates under the presumption you are marginally skilled in Thevenins theorem and the Maximum Power Transfer Theorem, and to a lesser degree, Norton's theorem and source conversion. If you're not familiar with these theorems and techniques, please take the time to check out those lectures, available at the Big Bad Tech channel. Our first task is to simplify this complicated two-terminal linear network supplying a variable load resistor into its Thevenin equivalent. This circuit is composed of a 16-volt source. Both R1 and R3 are 1 kΩ resistors, and R2 is a 2.2 kΩ resistor. By all means, pause the lecture and use Thevenin's theorem to simplify this complicated two-terminal linear network into a single Thevenins equivalent voltage source in series with a single Thevenins equivalent resistance. I'll start by solving for the Thevenins equivalent resistance. To solve for the Thevenins equivalent resistance, remove the variable load resistor. Next, remove the source. Since this is a voltage source, we'll replace it with a short circuit. Now we'll determine the resistance seen by an ohm meter attached to the two terminals formerly used by the variable load resistor. An ohm meter placed at node A and B would see R1 and R2 in parallel with each other in series with R3. The parallel combination of R1 and R2 is approximately 687.5 ohms. This in series with R3 would yield a Thevenins equivalent resistance of 1,687.5 ohms. Step 2. Now we need to solve for the Thevenins equivalent voltage. To solve for the Thevenins equivalent voltage, we need to remove the variable load resistor from the nodes of interest. Now we need to determine the open circuit voltage seen by a voltmeter attached to the two terminals formerly used by the variable load resistor. No current will flow through an open circuit. In this case, an open circuit condition would only induce current to flow through R1 and R2 and place these two resistors in a perfect series relationship. Since R3 has no current through it, there will be no voltage drop across it. The right end of R3, attached to our node of interest A, will have the same voltage as the left end of R3. For all intents and purposes, R3 can be removed from consideration when solving for voltage across the open circuit. In this case, the open circuit voltage would be equivalent to the voltage drop across R2. Let's use the VDR. The VDR is set up to solve for V2 is as follows. Substituting in the necessary values, we find V2 equals 11 volts. The Thevenins equivalent voltage for this circuit is therefore 11 volts. The Thevenins equivalent circuit for this previously complicated two-terminal network can be simplified into a series combination of the Thevenins equivalent resistance and the Thevenins equivalent voltage. In this case, an 11-volt source in series with a 1,687.5 resistor. Ideally, any variable load resistor attached to either circuit would be none the wiser to the substitution. That's the point. A Thevenins equivalent circuit is functionally equivalent to the previously complicated two-terminal network. However, is notably easier to solve for desired electrical quantities, being a simple series circuit. A single application of the VDR could be used to solve for the voltage drop experienced by any load. Ohm's law and the power equations can be used to solve for current and power experienced by any load. As a side note, if one wished to solve for the Norton's equivalent of this same circuit, one would solve for the Norton's equivalent resistance using identical techniques as previously used to solve for the Thevenins equivalent resistance. The Norton's equivalent current source value is determined by the current draw when short-circuiting the output terminals of the original circuit. However, since we've already solved for the Thevenins equivalent circuit, a simple source conversion of this voltage source in series with the resistance to a current source in parallel with the resistance would yield the same result. Either method would yield an approximately 6.52 milliamp current source in parallel with a 1687.5 ohm resistor. The Norton's equivalent circuit again yields a circuit notably easier to solve for desired electrical quantities, being a simple pure parallel circuit. A single application of the CDR could be used to solve for current drawn by any load resistor. Ohm's law and the power equations can be used to solve for the voltage across and the power experienced by any load. Compare and contrast the ease of the Thevenins and Norton's equivalent circuit to that of the original circuit when asked to solve for expected electrical properties experienced by the variable load resistor. By all means, pause the lecture and solve for the voltage drop across the load resistor, the current through the load resistor, and the power dissipated by the load resistor for 3 different conditions. 1 when the load resistor is a short circuit or has 0 ohms of resistance. 2 when the load resistor is an open circuit or has an infinite resistance. And finally at maximum power conditions when the load resistor equals the Thevenin's or Norton's equivalent resistance of 1687.5 ohms. Using the original circuit in short circuit conditions, the variable load resistor is replaced by a 0 ohm resistance. When RL is 0 ohms, it effectively places R2 in parallel with R3. The total resistance seen by the source is therefore R1 in series with a parallel combination of R2 and R3. The parallel combination of R2 and R3 is also 687.5 ohms. Therefore, the total resistance seen by this source is 1687.5 ohms. Ohm's law states that the source current will be equal to the source voltage divided by total resistance. Substituting in the necessary values, we find source current to be approximately 9.48 milliamperes. Source current must travel through R1, however splits between R2 and the path containing RL and R3 in series. The path containing R3 and RL in series is our path of interest. The CDR set up to solve for IL is as follows. Substituting in the necessary values, we find I3 to be approximately 6.52 milliamperes. This is the value of the Norton's equivalent current source we solved for previously using source conversion. In this condition, the 0 ohm load resistor experiences a comparatively large current draw. However, being a 0 ohm resistor, Ohm's law states that the load resistor will experience no voltage drop. This means during short circuit conditions, the power dissipated by the 0 ohm load resistor will be 0 watts. Consider how many steps it took to determine these values of voltage, current, and power using the original circuit. Now consider how quickly we can obtain these same values using the Thevenin's or Norton's equivalent circuit. Using the Thevenin's equivalent circuit in short circuit conditions, the current experienced by the 0 ohm load resistor will be attained with a single repetition of Ohm's law. Ohm's law states that the current drawn by the 0 ohm load resistor is approximately 6.52 milliamperes. The 0 ohm load resistor experiences no voltage drop. This means that during short circuit conditions, the power dissipated by the load resistor will be 0 watts. Using the Norton's equivalent circuit in short circuit conditions, the current experienced by the 0 ohm load resistor would be the Norton's equivalent circuit value. No calculations necessary. The 0 ohm load resistor would experience no voltage drop. This means during short circuit conditions, the power dissipated by the load resistor will be 0 watts. Part 2. Open circuit conditions. Using the original circuit in open circuit conditions, the variable load resistor would be replaced with an infinite resistance. No current will flow through the infinite resistance or open. In this case, current will only flow through R1 and R2 and place these two resistors in a perfect series relationship with each other. Since the path containing R3 and the infinite load resistance in series with one another has no current through it, there will be no voltage drop across R3. The right end of R3 will have the same voltage as the left end of R3. For all intents and purposes, R3 can be removed from consideration when solving for the voltage drop across the infinite load resistance. In this case, the voltage drop across the infinite resistance would be equivalent to the voltage drop across R2. The VDR set up to solve for V2 is as follows. Substituting in the necessary values, we find the voltage drop across our infinite load resistance equals 11 volts. This is the value of the Thevenin's equivalent voltage source we previously solved for. In this condition, the infinite load resistance experiences a comparatively large voltage drop. However, being an infinite resistance, experiences no current draw. This means during open circuit conditions, the power dissipated by the infinite load resistor will be 0 watts. Consider how many steps it took to determine these values of voltage, current, and power using the original circuit. Now consider how quickly we can obtain the same values using the Thevenin or Norton's equivalent circuits. Using the Thevenins Equivalent circuit in open circuit conditions, the voltage drop experienced by the infinite load resistor would be the Thevenins equivalent voltage value. No calculations necessary. The infinite load resistor experiences no current draw. This means during open circuit conditions, the power dissipated by the load resistor will be 0 watts. Using the Norton's equivalent circuit in open circuit conditions, the infinite load resistor experiences no current draw. All current will travel through the Norton's equivalent resistance in parallel. The voltage across the terminals would be attained with a single repetition of Ohm's law. Ohm's law states that the voltage across the two terminals would be 11 volts. The power equations state that the power dissipated by the load resistor will be 0 watts. Part 3. At conditions of maximum power, the load resistor assumes the value of the Thevenin's or Norton's equivalent resistance of 1,687.5 ohms. Using the original circuit, the variable load resistor is replaced with a 1,687.5 ohm resistor. The load resistor is in series with R3, a simplification I'll call R'. The R' branch containing the load resistor therefore has a resistance of 2,687.5 ohms. This R' branch is in parallel with R2, a simplification I'll call R'. R" has a resistance of approximately 1,209.7 ohms. R" is in series with R1. Therefore, the source would see approximately 2,209.7 ohms of total resistance. Ohm's law states that the source current will be equal to the source voltage divided by total resistance. Substituting in the necessary values, we find source current to be approximately 7.24 milliamperes. 7.24 milliamperes of current must travel through R1, however splits proportionally between the parallel paths provided by R2 and R', the series combination of R3 and load resistor RL. The R' path is our path of interest. Substituting in the necessary values, we find IL to be approximately 3.26 milliamperes. We can use Ohm's law to determine the voltage drop across the load resistor. Substituting the necessary values, we find VL to be 5.5 volts. We can use any permutation of the power equations to solve for power dissipated by the load resistor only. Substituting in the necessary values, we find power dissipated by the load resistor to be approximately 17.93 milliwatts. Again, consider how many steps it took to determine these values of voltage, current, and power using the original circuit. Now consider how quickly we can obtain these same values using the Thevenin's or Norton's equivalent circuit. Using the Thevenin's equivalent circuit in maximum power conditions, the voltage drop experienced by a 1,687.5 ohm load resistor in series with the Thevenin's equivalent resistance is half the Thevenin's equivalent voltage, or 5.5 volts. The Thevenin's equivalent resistance and the load resistance at maximum power conditions are equal resistances in series with one another and should experience the same voltage drop, the same current, and the same power. Any permutation of Ohm's law or the VDR will support this time-saving step. We can use Ohm's law to determine the current through the load resistor. Substituting in the necessary values, we find current through our load resistor to be 3.26 milliamperes. We can use any permutation of the power equations to solve for power dissipated by the load resistor only. Substituting in the necessary values, we again find power dissipated by the load resistor only to be approximately 17.93 milliwatts. Using the Norton's equivalent circuit, current draw experienced by the 1,687.5 ohm load resistor is half that of the Norton's equivalent current, or 3.26 milliamperes. The Norton's equivalent resistance and the load resistance at maximum power conditions are equal resistances in parallel with one another and should experience the same current draw, the same voltage drop, and the same power dissipation. Any permutation of Ohm's law or the CDR will support this time-saving step. We can use Ohm's law to determine the voltage drop across the load resistor to be 5.5 volts. We can use any permutation of the power equations to solve for power dissipated by the load resistor only to be approximately 17.93 milliwatts. If this has not convinced you of the utility and ease of Thevenin's theorem and Norton's theorem, I don't know what can. Every time the load resistor changes states, it necessitates another tedious series parallel circuit analysis if you use the original series parallel circuit. If, however, you utilize the Thevenin's or Norton's equivalent circuit, it is a simple pure series or pure parallel circuit that quickly and directly yields the desired values using the most basic of techniques. Realize we did this analysis for only 3 different values of load resistances. If we needed more data for more load values, I would personally dread yet another tedious slugfest through a sticky, tangled series parallel swamp and would welcome the ease and utility of the Thevenin's or Norton's equivalent simplifications. As an exercise, I leave it to you to solve for the voltage across, the current through, and the power dissipated by 2 different load resistor values. First load resistor is 1.5 kiloohms. The second load resistor is 1.9 kiloohms. Pause the lecture and solve for these quantities. Your choice, the tedious quagmire of 2 more series parallel circuit analyses, or a simple pure series circuit or pure parallel circuit presented by the Thevenin's or Norton's equivalent simplifications. I know my preferred choice. Again, I'm asking you to solve for the voltage across, the current through, and the power dissipated by the load resistor only. I don't care about the Thevenin's or Norton's equivalent resistor or the whole circuit. All I want to know is the voltage across, the current through, and the power dissipated by the load resistor only. If you're tracking, you should have obtained the following values. When the load resistor equals 1.5 kiloohms, the voltage across it should be 5.18 volts. The current through it should be approximately 3.45 milliamperes, and the power dissipated by it should be approximately 17.86 milliwatts. Notice when load resistance was slightly decreased from maximum power conditions, the current increased ever so slightly. However, the voltage dropped ever so slightly. The combined effects is that power at 17.86 milliwatts is ever so slightly less than the maximum power conditions when load resistance is slightly less than optimum. When RL is increased to 1.9 kiloohms, we find the voltage drop across it to be 5.83 volts, the current through it to be approximately 3.07 milliamperes, and the power dissipated by it to be approximately 17.86 milliwatts. Again, notice when load resistance was slightly increased from maximum power conditions, the current decreased ever so slightly. However, the voltage rose ever so slightly. Combined effects is that the power at 17.86 milliwatts is ever so slightly less than the maximum power conditions when load resistance is slightly more than optimum. That's the point. Maximum power conditions is when load resistance equals either the Thevenin's or Norton's equivalent resistance. Load resistances on either side will experience less than the maximum 17.93 milliwatts we calculated earlier. If we plotted power versus resistance data on a graph, we would expect maximum power condition to represent the peak of the curve. Regions where load resistance is on either side of the peak, like our 2 representative examples at 1.5 kiloohms and 1.9 kiloohms, would be in the shoulder regions of the peak power curve. Alright, I do believe we beat this example to death. Let's build the original circuit and see if we can experimentally determine the Thevenin's or Norton's equivalent values. Then we'll build the Thevenin's equivalent circuit and see how the original and the Thevenin's equivalent simplification respond to different load resistances. Ideally, they should behave identically. First, our original circuit is a series parallel combination of R1, R2, and R3. The terminals on the left-hand side are where the original 16-volt source is attached. The terminals on the right-hand side are where the adjustable load resistor would be attached. To experimentally determine the Thevenin's or Norton equivalent values, one must modify the original circuit and take observations using real-world instruments. First, to solve for the Thevenin's or Norton's equivalent resistance, one must remove the voltage source and replace it with a short circuit. Listen carefully. Remove the voltage source first. Then connect the 2 terminals it was attached to with a wire. Do not short circuit the voltage source. Doing so would cause your lab instructor to fly into a justifiably homicidal rage. Power off the voltage source and remove the voltage source. Then short circuit the original circuit. Now, remove the load resistor and measure the resistance seen by an ohm meter from the terminals of interest. The ohm meter indicates it's seeing a resistance very close to our anticipated value of 1687.5 ohms. Next, to solve for the Thevenins equivalent voltage, one must reattach the voltage source and remove the load resistor, and then measure the open circuit voltage using a voltmeter between the terminals of interest. The voltmeter indicates that the open circuit voltage of our original circuit is very close to our anticipated value of 11 volts. Finally, to solve for the Norton's equivalent current, one must remove the load resistor and measure the short circuit current using an ammeter between the terminals of interest. The ammeter indicates the short circuit current is very close to our anticipated value of 6.52 milliamperes. With this data in hand, we can now build either the Thevenins or the Norton's equivalent circuit. For the purposes of this exercise, we'll build the Thevenins equivalent. First, we'll use an adjustable potentiometer to make a 1687.5 ohm resistor. Next, we'll set up the voltage source for 11 volts. The 11 volt source in series with a 1687.5 ohm resistor is the Thevenins equivalent to our original circuit, and both these circuits should be functionally equivalent. Ideally, any load resistance would be none the wiser to the substitution. First, let's verify the functionality of the original circuit in 3 different scenarios. Once in short circuit conditions, again in open circuit conditions, and again in maximum power conditions. Here I'm using 2 DMMs. The top one is in ammeter mode and is measuring current through the load resistance. The bottom DMM is in voltmeter mode and measuring the voltage across the load resistance. The variable load resistor is a 2-terminal potentiometer placed across our nodes of interest. In short circuit conditions, when the load resistance is 0 ohms, the ammeter is measuring close to our anticipated value of 6.52 milliamperes and experiencing almost no voltage drop. Power delivered to this load resistance is essentially 0 watts. In open circuit conditions, when the load resistance is replaced with an open circuit, the ammeter reads no current draw, and the voltmeter indicates a value close to our anticipated value of 11 volts. In these conditions, power dissipated by the load is 0 watts. In maximum power conditions, when the load resistor is adjusted to approximately 1687.5 ohms, the ammeter reads a value very close to our anticipated current draw of 3.26 milliamperes, and the voltmeter reads a value close to our anticipated value of 5.5 volts. In these conditions, power dissipated by the load is very close to our anticipated value of 17.93 milliwatts. Now, let's verify the functionality of the Thevenins equivalent circuit in 3 different scenarios. Once in short circuit conditions, again in open circuit conditions, and again in maximum power conditions. The voltage source has been set up to 11 volt and a potentiometer has been adjusted to 1687.5 ohms. Again, I'm using 2 DMMs. The top one is in ammeter mode and is measuring current through the load resistance. The bottom one is in voltmeter mode and measuring the voltage across the load resistance. The variable load resistor is another 2-terminal potentiometer placed in series with our Thevenin equivalent resistance. That's the point. Not only is it easier to calculate electrical quantities using the Thevenins equivalent circuit, it's substantially easier to build. In short circuit conditions, when the load resistance is 0 ohms, the ammeter is measuring close to our anticipated value of 6.52 milliamperes and experiencing almost no voltage drop. Power delivered to this resistor is essentially 0 watts. In open circuit conditions, when the load resistance is replaced with an open circuit, the ammeter reads no current draw and the voltmeter indicates a value close to our anticipated value of 11 volts. In these conditions, power dissipated by the load is 0 watts. In maximum power conditions, when the load resistor is adjusted to 1687.5 ohms, the ammeter reads a current value close to our anticipated draw of 3.26 milliamperes, and the voltmeter reads a value close to our anticipated value of 5.5 volts. In these conditions, power dissipated by the load is close to our anticipated value of 17.93 milliwatts. If one was to start at short circuit conditions and progressively increase resistance, recording voltage and current values at each step, we would obtain the following graphs. Notice as load resistance increases, current through the load decreases, and voltage drop across the load increases. I've taken the liberty of zooming in on the second graph to a region highlighting voltage and current properties for resistance values close to maximum power conditions. The graphs on the right form the product of the observed voltage and current values at various resistance values. Notice the power curve peaks out in the region of 1,687.5 ohms as expected. Again, if we zoom in on an area close to maximum power conditions, we can see the behavior of the peak. In conditions of maximum power, power peaks out as expected. Regions on the low side shoulder of the peak experience more current draw but less voltage drop. Regions on the high side shoulder of the peak experience more voltage drop but less current draw. The maximum power point is a compromised condition in which two interrelated voltage and current values form a maximum power product. Alright, I believe we accomplished what we intended to do for this lecture. In conclusion, we use Thevenin's theorem to simplify a complicated two-terminal linear network supplying a variable load resistor into its Thevenins equivalent circuit of a single voltage source in series with a single resistor. We next predicted the response of these circuits to varying load conditions. Finally, we verified our calculations by building both the original circuit and the Thevenins equivalent circuit using real-world components and observed their functionality with varying loads using common electrical instrumentation. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.